So if you perform a trace on this function, you can see that it does cross only once, and it only crosses at 4, let's see, at 4, 0 is where it crosses. And so what I'm going to do is I'm going to just use synthetic division and put 4 in the box. I'll put the coefficients here, 1, -4, 4, and -16. And I'm just going to synthetically divide out 4. I know it's a solution because I saw it on the graph. So I add really for what 4 times 1 is 4. Add to get 0, 0 times 4 is 0. Add to get 4. 4 times 4 is 16. And there's no surprise there that this remainder ended up being 0. I expected that. And now I can put this as a constant, this is an x term, this is an x squared term. My factor, when I write it out, would be x squared plus 4. Okay, so that's my factor. My other factor, if I want to write it, really comes from this. If the solution is 4, the factor would be x minus 4. Right? And so I could factor this polynomial, this times this. These are factors by the factor theorem, since the remainder is 0. This is definitely a factor. And it says find all the roots. So to find all the roots, all you do with this is basically say, well, what are my 2 roots? Well, x equals 4. I already knew that was a root. I got that one from the graph. And then just set this factor equals 0. So x squared plus 4 equals 0. So x squared equals -4. So take square to both sides. Don't forget, plus or minus. If x equals plus or minus and square root of -4, I hope you know is 2i. So we had 2 imaginary roots there. And so sometimes you get imaginary, sometimes you get irrational, but if you get the rational roots out, you should get it down to a quadratic here. Once you get it down to a quadratic, you can use quadratic formula. You can set it equals 0 to solve, whatever way is easiest for you to do at that point. So my solutions are 3 solutions, 4, and plus or minus 2i. And that's no surprise. We knew that we're going to have 3 solutions for this problem. Let's just look at another one. This one's to the 4th power, so get your calculator out and go ahead and type in this function. Okay, so I graphed this in my T-Inspire, and I got a couple of roots here that look kind of nasty at 1.73 and -1.73, but I really like these 2 roots, 5 and -1. It crosses at 5 and -1, and those look like nice rational roots. Let's just double check. Let's do our whole rational root theorem, just make sure what happens here. So factors of 15 up top, 15, 5, 3, and 1. Factors of 1 in the denominator. So my possible rational roots would be plus or minus 15, plus or minus 5, plus or minus 3, and plus or minus 1. If there are rational roots, they would come from this group, and you can see -1, and 5 came from this group here, so that's no surprise. So let's start with our original polynomial, and let's divide out, synthetically divide out. It doesn't matter which one you choose first. I'm going to choose -1. And so there's 1, -4, -8, 12, and 15. I know my remainder is going to be 0 because this is a root. So it kind of helps to run around the front end here. We're going to do this in type division. This is 3, 15, and -15. 0. So my remainder is 0. Yay. At this point, the best thing to do is I've now taken this from x to the 4th power. This term, this would be, let's see, x squared, x third. This is an x to the 3rd term. If you start with 4, I let you get 2 rational roots from the graph. Get it down to a quadratic, and then you'll have to use like quadratic formula or something like that to solve. So now I'm going to take the 5 out. The shortcut way to do that is just do another synthetic division now, starting with your answer. I'm trying to get this answer smaller than x to the 3rd, what it is right now. So I'm going to put 5 in the box now. And when I work this out, this should work. 0, 0, -3, negative 15. Remainder is 0. Alright, my remainder is 0 again. That's a great sign. Things are working out. So let's think about what this represents. This is a constant, this is x, this is x squared. So at this point, I've got a factor here. I've got x squared minus 3. I've got a couple other factors if I wanted to write them. This is x minus 5. Oops, x minus 5, that comes from here. And of course we have x plus 1, and it comes from the negative 1 there. So those are my factors for the polynomial. If I set that equal to theorem, solve. I get x equals negative 1. I got that one for the graph. X equals 5. Got that one for the graph. But this, I don't know what the solutions are. So I'll need to, again, in this case, I can just set it equal to 0. Sometimes I have to use quadratic formula. I'll just set equal to 0. X squared equals 3. Square both sides, don't forget. Plus or minus x equals plus or minus square root of 3. So I found 2 irrational roots and 2 rational roots. These two I found from the graph, and I allowed to do that rather than testing synthetic division on all 8 of those possibilities. I went ahead and let you just kind of, it's not quite cheating, it's just I'm allowing you to do that to get some of those from the graph. Again, this problem is the same as the one we just did. I think I'm going to skip it. This is what I want to get to. The last 3 problems in your homework are Descartes' rule of signs. The number of positive real zeros is equal to the number of variations in sign that is less than that by the even numbers. Okay, so what in the world is this theorem talking about? It's just kind of an obscure theorem. It's one that was really helpful before we had calculators, before we could graph things really, really quickly. Now we don't really need this theorem that much, but I'm still going to make you learn it, just because it's got some neat math in there. It doesn't figure out a whole lot of for sure things, but it does figure out some possibilities, and if you're doing some graphing by hand, it can help us figure out where it crosses the x-axis, or at least where it could cross the x-axis. So when it says this, positive real zeros, what that means is, let's say the graph crosses something like this. Maybe crosses here. This point is a negative real zero, right? It crosses where the x value is negative. I don't know what that x value is. I don't have a scale on this graph, but it's definitely negative. These 2 values are positive real zeros because the x-axis is positive as you go to the left, right, and negative as you go to the left. So these 2 are positive real zeros. The number of positive real zeros is either equal to the number of variations in sign. So let's see what variations in sign are. So this is what I mean by that. So this term is positive. When I go positive to positive, there's no sign change. Right? There's no sign change from here to there. Both terms are positive. Oh, positive to negative, I see a sign change right there. Right? Positive, negative. Negative to negative, no sign change. Negative to positive, I see a sign change. There were 2 sign changes in this polynomial. So what that tells us, there are 2 variations in sign. So there are 2 possible, it's an interesting thing, it doesn't tell us for sure there are 2, positive real zeros on this graph. Oh, and it says one more thing. Or less than that by an even whole number. What's an even whole number less than 2? Well, 2 minus an even number like 2 is 0. So there's actually 2 possibilities here. There are either 2, maybe the graph looks something like this, positive real zeros, or maybe the graph kind of looks like this, and it doesn't cross the positive x-axis at all. Maybe it has a negative real zero right here, but no positive real zero. So that's the other possibility, 2 or 0 possible real zeros. Okay. To find the negative possibilities, all you do is plug in negative x and simplify. When I say simplify, I mean kind of determine whether it's always positive or always negative. So when I plug in 2 times negative x to the fourth plus 3 times negative x to the third minus 5 times negative x squared minus 2 times negative x plus 7. Now let me just evaluate which terms are always positive or which terms are always negative. And this, I hope you agree, a negative to an even power will always be positive. So this is really just 2x to the fourth. That's a positive term. A negative to an odd power will always be negative. So minus 3x to the third. A negative to an even power, this part of this will be positive, but there's still a subtraction there. So we have minus 5x squared. Subtracting a negative will be like boom, boom, adding a positive there, and plus 7. You may notice that these, with even ones, turn positive, and these, the odd ones, turn negative. So they change the sign. If you look at the original, this one changed sign from positive to negative, and this one changed sign from negative to positive. But you notice the even ones really stayed the same. So the only two things that changed were these two. Okay, so let's redo the number of sign changes. To find the possible negative zeros, this is what we do. So I'll count it out. So let's see, positive to negative, that's one sign change. Negative to negative, no sign change. Negative to positive, that's a sign change. And positive, positive, no sign change. So there are two possible negative real zeros. Or less than that by an even number, so 2 or 0 possible negative reals. When you look at this problem, you know there are 4 solutions. Right? You know there are 4. It's 2x to the fourth power. So one possibility is there's 2 positives and 2 negatives. The other possibility is there's 0 positives and 2 negatives, or you could have 0 positives and 0 negatives here. So there's a number of different possibilities there. In fact, if you wanted to, this would be really good if you can understand this part, which is basically how many imaginary or complex roots will we have? Well, I know we have a total of 4. So if this is 2 and this is 2, I'll have 0 imaginary. That's a possibility. If this is 0 and this is 2, and there's a total of 4, well, I might have 2 imaginaries. That's possible. If this one, because it's possible that there's 0 positives, it's possible there's 0 negatives, 0 and 0, I still have 4 left. So I could have 4 imaginaries. A couple things about imaginary roots. So there are 4, 2, or 0 imaginary roots. I don't know how many. This theorem doesn't tell me for sure things. It tells me possibilities. And so with the imaginary roots, they always come in pairs. Remember, they always travel together in the mall. They always dress alike. They look alike. And so they always come in pairs. You'll never have like 1 imaginary root possibilities or 3 or 5. Those aren't possible. You would only have even number possibilities there. And that's basically the Descartes' rule of signs. We'll probably go over this a little bit more in the next lesson just to make sure you're kind of getting it. But that's sorry this lesson was so long. It's kind of a lengthy lesson. So it was something that it just took a long time for the screencast.